Hello everybody, welcome back to another discussion in dynamics. Today we'll start a new topic called normal tangential coordinate system. And we'll start our discussion with a brief lecture review, and then we will just do one example. Sounds like a plan for today? Let's do it then. So here is my brief lecture review. As you can see, I prepared something before coming here, yes? And today I will focus on explaining how to describe the motion in a normal tangential coordinate system, okay? And I think that the best way to do it is if we compare that new coordinate system to the one we already know, called Cartesian coordinate system, okay? So let me spend like 1 or 2 minutes on Cartesian coordinates, okay? So what is specific about them? These two vectors, right? I and j. And why they are so important? Because regardless of anything, they do not change in time. I points always in that way, and j always points in that way. And that's why describing the motion of a particle, p, that follows this trajectory is quite easy most of the time. If we use these coordinates, right? So how we do it? We usually start with position, yes? So we take Cartesian coordinate system, we express position in them in that way. And then, if we would like to know what is the velocity of a particle, we take first time derivative of that position. And we end up with velocity, and then we take one time derivative again, and we have acceleration expressed in that way. And also we have two notations, right? We have US notation. If you want, you can use it if you find it comfortable. I find comfortable my favorite notation. And why? Because it is my favorite notation. Yeah, so that was 1 or 2 minutes on Cartesian coordinate system, and now let's focus on normal tangential coordinate system. So, to describe the motion in that coordinate system, we use two new unit vectors called ut and un. They are unit vectors, but they are not constant. They are no longer constant. Not constant, sorry. By not constant, I mean that they are, if we take first time derivative of ut, this won't be zero vector. Also, if we take first time derivative of un, it's also not a constant vector. It's not going to be zero. In opposite to what happened earlier, right? If you allow me, if I can scroll down the board, if we take di dt, that was indeed zero. Yes, because I is a constant vector. By the way, d dt of anything constant, for example, a constant vector, will result in zero. Yeah, but in this case, it will be zero vector. Because the object is constant, object does not change in time. Okay. So what I would like you to do, I would like you to imagine exactly the same situation that we had last time. We have exactly the same particle that follows exactly the same trajectory. Okay, the motion is exactly the same. Why I am talking about that? Because the only thing that will change is the description of the motion. Yes, we can describe the same motion in different ways. Yes, in Cartesian coordinate system, or in tangential coordinate system. And so if we have the same motion and we would like to describe it, so let me just put here that trajectory is exactly the same. Okay, trajectory exactly the same. The same as before. So then in nt coordinates, we actually start from velocity. Okay, so velocity at point P will be pointing this way. Okay, and if we would like to express it using ut and un, we should probably write it in such way. Something times ut plus something times un, right? So let me introduce ut in the board. Ut is by definition always aligned with velocity. By definition, velocity is always parallel to ut. So guys, with such defined ut, could you please help me and could you please tell me what I should put in here? What are the components of v? Anybody? Perfect. And why? Because it is indeed aligned with that unit vector. So Sean said that I should put here v and 0 in here. Perfect. This is true. So if the second component is 0, I'm just gonna erase that component, okay? I'm gonna erase it. Great. This is our definition for v. So now let's go one step further. Let's go to acceleration, yes? And as I told you earlier, definition does not change, yes? A is first time derivative of position. So let's plug that expression Sean told us in this formula. So in here we have d dt, v ut. Yep, and this is none other than product rule. Yep, so I can actually write dv dt ut plus v dut dt. Okay, and just as I told you earlier, just to save some ink, this will be v dot from now on. And believe me or not, but this expression is equal to v divided by rho un. Okay, believe me or not, but the derivative of ut is v divided by rho un. In the past, I was actually deriving that, during the discussion. But honestly, it's not. You are not required to understand the derivation. Okay, the only thing you are required to do is to know how to use these expressions. Okay. However, if you are interested in seeing the derivation, please stop by my office hours. I'm very happy to derive that expression for you. Okay, or you can stop by office hours of anybody else. Yeah, there are like 6 of us responsible for that course. Yeah, so you can choose your favorite person, and you can go and talk to them. Okay, so let's write it in such way. So our acceleration is expressed in such form: v dot ut plus v squared rho un. Okay, so we have definitions for velocity and acceleration in a normal tangential coordinate system. So far, so good? Because I think I owe you 2 things. Yes? First of all, I owe you un. Yes? and then I will also tell you what rho is. So let me scroll up the board. I will put un on the drawing. So un is also unit vector. It is for sure perpendicular to ut, and it points inside the curvature. Okay? So in that case, at that, let's say, time instant 4, let's time instant 4 seconds, our un will look like that. But let's imagine that at time instant, let's say 7, our point P is here. Yeah, at time instant 7, our point P will be here, and its velocity will be following. You see, because it has to be tangent to the trajectory, right? So now let me draw ut. Ut must be aligned with velocity, and un must point inside the curvature. Okay, guys, do you see that these vectors indeed change in time? They change the direction, yes? At time instant 4, ut was pointing this way, yeah? At time instant 7, ut is pointing that way, yeah? It changes in time. That's why their derivative is not 0. Okay, now, so far so good? Any questions? Am I making you more confused? No? Okay, cool. Okay, so I gave you un. And I said that I owe you also rho. So what is rho? I'm about to tell you, but maybe some of you can tell me. Yeah, what do you think rho is? Yes, sir? Yeah. That imaginary circle, yeah. Because you said that it's a radius of a curvature. Is that correct? Is it just a correct way to say that? I thought only a circle can have a radius. Yeah. And you said it's like a radius of a curvature, yeah.
No,
so
that's what he said during the lecture.
Yeah. So maybe it's like a shortcut, yeah. Anyway, what I'm talking about, it's like a radius of that imaginary circle that is tangent to the curvature, yeah. And can circle be tangent? No. Yeah. Anyway, that circle, that imaginary circle has actually its name. It's called osculating circle. Yeah. So anyway. And that osculating circle tells us how sharp is the turn. Okay, so let's see at time instant 4. That turn, our particle P, turns kind of, that turn is kind of sharp, yeah? So our osculating circle will be small. So at this point, this is our osculating circle. And radius of it is exactly rho. Radius of that circle is rho. Oh, sorry. And how about time instant 7? That turn is not that sharp, yeah? Our particle turns, but it's rather smooth turn, yeah? So that osculating circle will be huge there, okay? It can be even something like that. So at this point, our osculating circle will look like that, okay? And our rho will be larger here. I can put rho maybe here. Our rho of that circle will be a little bit larger, okay? So that's the theory behind that rho. First of all, you have to have that osculating circle or imaginary. I actually like your term. That's that imaginary circle, and then radius of that circle is our rho. Yeah, and the smaller it is, the sharper the turn is. Okay, and as you can see, rho also changes in time. Yes, rho is at the beginning a little bit smaller, and then it gets larger. Yes, and then it will get smaller again. Yes, so it changes with time and space. Okay, now. I'm doing everything to make you confused. Are you confused? Was that explanation okay? Cool. So actually that's all the theory I wanted to cover today. Yeah? Any questions? Don't be shy. Okay, you don't have to ask questions right now. If you have a question later, you can ask me later. Before doing our example, I wanna actually do one more thing, yeah? Because we found our expressions in US notation, but we can also express them in a vector form, yeah? So our V can be actually expressed in such way, V, 0, 0. But if I do that, I must indicate that I expressed it in NT coordinates. Yeah? So in here, I will write UT, UN, K. Okay, so that vector is expressed in this coordinate system. How about A? A will have such form. V dot, V squared over rho, 0. And I'm going to have a shorthand notation, okay? So in here, I will just put T, N, and K. Okay, so by doing that, I just indicate the coordinate system I'm expressing my vector in. Yeah, that's clear? How about their magnitudes? Yeah, magnitude of V is clearly V. Yeah, it has only one component. Yeah, so our magnitude of V is just, I don't know, it's just V. Yeah. How about A? Yeah, if we would like to express magnitude of our acceleration, I think we should go for our old good square root. Yes. So it will be V dot squared plus V to the power of 4 divided by rho squared square root. Yeah. So if somebody asks you, give me magnitude of acceleration, and the acceleration is expressed in anti-coordinates, just go for that expression, okay? And now I'm seriously done with everything I wanted to say. And again, Mike is yours. Yes, Jaden?
How come there's no expression for the position in normal tangential?
Oh, that's a good question, actually. Yeah. How about you answer that question? Yeah. So.
Because it's always changing.
Yeah.
It still seems like there should be.
Yeah, that's a great question. Yeah. So Jaden asked how to express position in this coordinate system. Yeah. So let me get rid of these oscillating circles, okay? And Jaden, so the question, you asked a question, but you actually know the answer, I think, yeah? So question for you is that, wait, sorry. How would you express, this point in this red coordinate system? What are coordinates of point P? In this. Okay, no worries, you don't have to know, yeah. But I think that somebody will know, yeah, because we have like 700 people here, yes? So guys, the question is, what are the coordinates of this point, P, in that red coordinate system? Anybody? Yes, and your name is Daniel. Yeah, it's 0 because it's aligned, you see? Yeah. By the way, what are the coordinates of this point in this coordinate system?
Also 0.
0, yeah. So it is always 0, yeah? So I can actually write that this is 0 always, yeah? So I think this is how we write it in mathematically, yeah? Like 3 horizontal lines, yeah? If it's a constant number, or, yeah. So, but actually, so it's always 0, or we just don't define it, yeah? Because we know that it is always constant, it is 0, yeah? So,
That makes sense.
Cool, thank you for the question. Or we don't define it. Yeah. Okay, guys. Any other question? So what do you want to do? This is all I wanted to say today. Yeah. And now we can do example number 1. Yes, let's do it. All right. As usually, please take a couple of seconds to familiarize yourself with the problem statement before we start our solution. Okay, so what do we have in here? We have our particle so first of all, we have our drum, yes? So this is our drum. Yep. That drum has radius r, and we have a particle here that is constrained by a string, and that string, while that particle is moving, that string wraps around the cylinder, right? So I believe the trajectory of that particle will look like that. Please tell me if you agree with me. I think that the trajectory will be something like a little bit of a spiral. Yeah, the trajectory will be something like that. And what else do we know? We know that velocity of that particle is constant and always equal to v0. And we also know the initial length of the string, that is L0. And we also know that angle theta that I'm going to define right now. So basically that angle theta defines where is the touching point, the first touching point between the rope and the drum. Yeah, so this is our theta. Okay, guys, so let's summarize what we know. Nonce, we know that V is constant and equal to V0. And also we know radius of a drum. We know that initial length is L0. And let's say that we know the variable theta, okay? And what they ask us to find? First of all, in part A, they ask us to express A in ut and un. And then in part B, they told us that once we solved part A, they want us to express A in I and j. So that's our goal for today. Any questions about the problem statement? So this is my solution. And this is how I approach such problems. First of all, I just take ready-to-go expression we derived on the previous board. So our acceleration on the previous board was equal to dv dt times ut plus v squared over rho un. And I just fill it out. So basically our goal is to find values or expressions for this and that. And I usually call it AT and AN. Okay. So our AT will be equal to something and our AN will be equal to something. Interesting. Okay, so AT is equal to dv dt. And what is it? A little bit louder? It will be 0, yes? And I'm not going to even ask you why, because everybody knows that that velocity is constant, yes? Because velocity is constant, right? So basically we can get rid of this component. Yeah, that component we can eliminate. How about AN? So our AN is equal to V squared over rho. And I think that you guys told me that V is equal to V0 squared. And now the question is, what is rho? What shall I put in the denominator? Yeah. So rho is equal to question mark. Okay. And again, I would like to give Mike into your hands. Could you please tell me what is rho? Yeah, Sean? It is. That's true. Sean is right. Yeah. So Sean said that rho is equal to L naught minus R theta. Yeah. How do you know that? How did you figure it out? Yeah. Because in here we I don't want you to throw equation at me. Yeah. What's the thinking process? Yeah. And you should start, that's everything history, and you should start your answer with saying that rho is this length. This is rho, basically. Yeah, the length of the rope is rho. Yeah. So Sean noticed that our rope does not change its length. Yes. L0 is constant. Yes. So he just noticed that we can write L0, and L0 is so L0 is L0 at time instance 0 at the beginning, yes? But then at this point, our L0 will consist of two chunks, that green one and this orange one. Yep. So, and this is arc length. That orange arc length is exactly r theta. Yep, exactly. So I can even use some colors to explain it. Yeah. So L0 was rho plus r theta. Yeah, and that's how Sean obtained rho, and he was right. Cool. So let's follow his suggestion and let's plug our rho in here. So this will be L0 minus r theta. Okay, and you guys solved 100% of the problem, because right now we can just write that our A is equal to V0 squared L0 minus r theta times un. Yeah, this is answer to our problem. Yeah, if you like my favorite notation, yeah, you can write 0 v0 squared L0 minus r theta 0. And of course, let's not forget about this subscript, T, N, K. Okay, so this is answer to part A. Okay, guys, how does it look like from your perspective? And thank you for help, by the way, everybody. Yeah, it is a little bit abstract concept, right? Yeah, you have to like exercise your brain a little bit to understand it. Yes, but I am more than sure that all of you can do it. Yeah, just use this thing and it will be fine. So what now? Questions or part B? Yeah. Okay, let's do part B. Part B. All right. So they told us that they would like us to express A in I and J, yes, and so in other words, they told us to jump from Tn, yep, into I and J. We're gonna do that jump from here to here. Okay. So I'm gonna steal this drawing, okay? Somebody drew it yesterday. It's a good drawing. I'm gonna steal it here. Oops. Why you are not listening to me again? I'm talking to my computer, of course. Okay. But we don't need all of the drawing, yes? So I will just erase some stuff. I think we don't need that. I think we don't need this. We definitely don't need that. And this orange stuff is going out for sure. Bye-bye to that, bye-bye to that. And I think that we can also get rid of this. So we just need that. Okay, guys. So, wait a second. Bye-bye to that as well. Okay, now I'm ready to do part B. Okay, guys. So you told me that this is expression for our acceleration, right? So let me draw it in anti-coordinate system, okay? So I bet that un will be pointing this way, and ut will be pointing this way, yes? And they are, of course, perpendicular to each other, yes? Okay, and A is aligned with un. So our A will look like that. This is our A. Okay, and they would like us to express A in such form. Something times I plus something times J. Yep. Okay, so we just need to project it, yes? It's just a simple projection, yes? So we basically have to project this green vector onto, onto this component, onto this direction, and onto this direction. And we can go home. Yep. Okay, so we just need this blue component here. Let's call it AX. And we also need this blue component here. Let's call it AY. Okay, and in order to do projections, I probably must bring this theta somewhere closer there, yes? I need to bring that theta somewhere closer to these triangles, okay? So how can I do that? Maybe let me introduce such directions also. This direction, this direction. Am I able to do it right now? Not really. Maybe also I would like these directions to help me. This one and this one. Okay. So I'm pretty sure that if theta is here, then theta will be here for sure. Right? And if theta is there, theta will be here. So that means that this guy here is 90 minus theta. So that means that this guy is theta, that theta is here. Any objections? Yeah. Okay, so again, mic will be yours, as usually in such cases. AX is a sine or cosine? Yeah, it's sine, yes. Sine. Sine theta, and AY has no other choice. AY will be a cosine theta. Okay, so the problem is done. Yeah, so our A has such components. A sine theta minus a cosine theta. Thank you, guys. Yeah. But I think we know expression for A. Yeah, we know expression for A because A is just a magnitude of this vector, yes? So A, I can write it here maybe. A is just a magnitude of vector A. So it would be equal to this expression. Right? So I can actually write that our A is equal to, I think, V0 squared divided by L minus R theta sine I minus cosine j. Yep. Or in the vector notation, you can write a as a v0 squared, l. Oh, I think I forgot about l naught. Yeah, I forgot about 0 here. 0 and 0 here. And 0 here. Minus r theta times this vector. Sine theta minus cosine theta 0. And also theta is missing here. Okay, guys. Am I asking you like, do you have any questions too many times? Or is it annoying? No?
No.
Yeah. So do you have any questions? How much time do we have? Oh, we still have 9 minutes. So that's the end of the problem, yes? So these are our answers. This is just a side note. So let me put this one here. Let me put this one here, maybe. Okay, so this is the end of the discussion, but I want to do one more thing. Okay, so I just want to say that these are the answers. Yeah, this is the answer. This or this, whichever notation you prefer. This is answer B. Answer B. Okay. Yeah, because we indeed expressed A in I and J coordinate system. Yeah. So if you really want to be pedantic, you can put I and J and K in here, just to tell the reader that this is expressed in I and J. But you don't have to. Okay, so during last 7 minutes, I wanna draw something. I wanna draw a cat, maybe. Yeah. No, I'm kidding. I wanna draw a function. I wanna draw a function this function a expressed as a function of theta. Okay. Oh, this is theta. Yeah. This is theta. And this is our expression for that a. By the way, about drawing cats, do you know that there is a website, I wanna draw a cat for you? Have you heard about it? Is there anybody who heard about it? I wanna draw a cat for you. Yeah, go for it. It's actually pretty funny. Yeah. So anyway, do you know what Shark Tank is? Where entrepreneurs or entrepreneurs to be come in front of the experienced entrepreneurs and they just show their idea and they ask for investment in return for some percentage of their company. Yeah, so that guy was there, actually, the owner of I Wanna Draw a Cat for You, went there and he actually got investment. So yeah, watch it on, I think it's on YouTube. If you draw I wanna draw a cat for you, Shark Tank, you can see his speech. Yeah. It's hilarious, actually. So, yeah, if you don't have anything to do today, do it. I'm a big fan of that show, by the way. Yeah. I'm a big fan of actually entrepreneurs. I really like, and I think that I would like to try my luck there as well. Anyway, yes, that website is about drawing a cat. So you can ask that, you can pay that guy $10 and he will draw a cat for you. Yeah. Yeah, if you want, you can do it. Yeah. Or you can just, pay him $10 and you can like say him, hey, can you draw a cat for Kaylee? Or something. Yeah. And if you want him to draw a cat for you, I think that he's busy for the next 3 months, actually, because so many people want him to draw a cat. Yeah. Anyway, this is not about cats. This is about dynamics. Yes. Let's go back to our discussion. So I want to draw a function. Yes. Yeah. That guy draw cats. I draw functions for living. Yes. Okay. So I want to draw a function of a. And the argument is theta. Okay, and this is our expression. So this is a hyperbolic function, yes? It is a hyperbolic function, yeah? Okay, so what value it will have for theta 0? What's that value? Yeah, exactly, L0, yeah. V naught squared over L0, yeah. And I think that somewhere here we will have an asymptote, yeah? Let's call it like, I don't know, theta star, I don't know, or theta heat, yeah? Because this is where heat will occur, yes? So at that theta, heat will occur. Heat. Yeah. So I can scrub the board maybe for a second, guys, okay? So that theta heat will be obviously here. Yep. This is our theta star, because this is where heat occurs. Do you see that? Yeah. So can you give me expression for theta star? What's theta star? I understand. So give me the expression.
L0 equals R theta.
L0 divided by, yeah, over R. Yeah, so it will be L0 over R. Yes, because in here our denominator has to be 0. Yes, so the requirement for that is L0 minus R theta star must be 0. Yes, the denominator must go nuts. Yes, yeah, and if you solve that expression for theta star, you will obtain this expression. Okay, so let's draw it, and we can call it a day. So our function will look like that. Yeah, you guys can clearly see that our acceleration increases, and right before the heat, it will go to infinity, right? Yeah. Yeah. So our drum will be hit with large acceleration, even though velocity is constant. Yes, velocity of the particle is constant, but acceleration is not, because it turns drastically. Yeah, right before the heat. Okay, I think I really have nothing else to say. We covered everything. Thank you so much for today. Yeah, and see you next time. Yeah, bye.